Those who have joined the class can give their attendance in the chat box. I repeat, those who have joined the class can give their attendance in the chat box. So it is 2:15 p.m. I will not wait further. Just give me a minute so that I can present my screen. Can anyone respond whether my slides are visible or not?
Yes, sir, visible.
Okay, thank you. So, if you remember, in the last class, we did some problems related to Rayleigh-Ritz method. With that problem, we ended up the first module of this course. Today, we will start the second module of this course, and the very first topic in the second module is the determination of stiffness matrix by potential energy approach. Basically, this, just wait for a minute, somebody is joining. Okay. Basically, this potential energy approach in FEM is a vast topic. So, what they have did is they have kept half portion in the first module and the remaining half portion in the second module. Fine. So, the very first topic of the second module is the determination of stiffness matrix by potential energy approach. If you remember, in the first module, I think after first or second class, we have solved one problem. We have taken one cantilever beam. On that cantilever beam, we have applied an axial load and we have found out the stiffness matrix for that cantilever beam. Similarly, here also, for some problems, we will be finding out the stiffness matrix, but we will be using which method? We will be using potential energy approach method. Is it okay? Hello? Is it clear?
Yes, sir.
Okay. So let us take an example, and by this example, let us try to understand how we can determine stiffness matrix by potential energy approach. What is given in the problem? The problem tells you that obtain the assembled stiffness matrix of the given arrangement of spring system using the principle of potential energy approach. That means three springs is given to you and all the three springs are connected in series. Both the end of the spring, both the two extreme end of the spring are fixed. So it is also given to you that this spring, the first spring is having a stiffness value of how much? K1. Second spring is having a stiffness value of K2. And the third spring is having a stiffness value of K3. It is also given in the problem that this is nodal point 1, this is nodal point 2, this is nodal point 3, this is nodal point 4. That means there are total 3 elements present. This is your element 1 connecting node 1 and 2. This is your element 2 connecting node 2 and 3. This is your element 3 connecting node 3 and 4. Let us assume that the linear displacement due to the, by looking at this arrangement we can see that the spring can linearly displace along x direction. So let us assume that u is the linear displacement. Fine. Then node 1 is having how much displacement? Assume that the node 1 is having a displacement value u1. Node 2 is having displacement value u2. Node 3 is having displacement value u3. And node 4 is having displacement value u4. Also, it is given in the problem that the force acting at each nodal point of the individual spring element is given by, at node point 1 force acting is F1 along positive x direction, at node point 2 force acting is F2, at nodal point 3 force acting is F3, and at nodal point 4 force acting is F4, and all the forces are along positive x direction. Is the diagram clear to you? Any doubt in the diagram?
No, sir.
Okay. So what I need to find out? I need to find out the assembled or the global stiffness matrix. Global stiffness matrix or assembled stiffness matrix means the entire stiffness matrix for the problem, considering all the three elements together. That we need to find out. If you remember, I think on the second or third class, we have found out one stiffness matrix for a cantilever beam in which an axial load was acting, but by algebraic method. But here we have to use which method? We have to use the principle of potential energy approach to find out the value of that stiffness matrix. How we can find out? For that, the very first step is what? The very first step is you have to write down the potential energy or the potential function for the complete problem. We know that the potential function or potential energy or simply the potential of the problem is given by summation of all internal energies present in the problem plus summation of all the work done due to external force present in the problem. And we know that the internal energies present in the problem is nothing but the strain energy stored in the problem. Let us denote strain energy by symbol U. And what is W? W is nothing but the total work done due to external forces, and we know that the total work done by external force is always negative in nature, so the final expression of pi becomes pi is equal to u minus w. Is it clear so far? Any doubt so far?
Sir, clear, sir.
Okay, so in order to find out the potential for this problem, I need to evaluate the value of strain energy stored in the entire problem plus the external work done in this entire problem. So let us find out the strain energy stored in the problem. If you remember, some 2-3 lectures back when I was discussing this Rayleigh-Ritz method, Galerkin method, I have told you that strain energy in case of spring is given by what? It is given by U is equal to half into stiffness of the spring into the linear displacement of the string square. That means half k into delta square. If I assume that delta is the linear displacement of the spring, if I assume that, say, for this particular element, deflection is delta 1, For this particular element, linear deflection is delta 2. For this particular spring element, linear deflection is delta 3. This delta 3 is due to the presence of F4 and F3 in this component. This delta 2 is due to the presence of force F2 and F3 in this component. And this delta 1 is due to the presence of F1 and F2 in this component. Then overall, we can write the strain energy U is equal to what? Half K delta square, where K is the stiffness of the individual spring and delta is the linear displacement. According to this problem, displacement will be linear. In some other problem, displacement can be vertical, fine. So we can write this, since there are three elements. This is element number 1, this is element number 2, this is element number 3. So there will be total 3 strain energies will be associated with this problem, and is given by U is equal to half for this particular element K1 into delta 1 square. What is delta 1? Delta 1 is the linear displacement for element 1. For second element, it is plus half K2 into delta 2 square. What is delta 2? Delta 2 is the linear displacement for the second element, plus for the third element, it is half K3 delta 3 square, where delta 3 is the linear displacement of the third spring element, which is equation number 2. Is it clear? Equation number 2. Any doubt in equation number 2? Any doubt in equation number 2 so
No,
far?
sir.
Okay. Now, if you see in equation number 2, equation number 2 is what? It is a function of delta, because K1, K2 and K3 are what? K1, K2 and K3 are the stiffness of the spring, which is a constant value. What is changing continuously? Deflection of each element is changing continuously due to the change in the nodal forces. So that means in this equation number 2, if I want to find out the final expression of strain energy stored in the problem, I need to evaluate the linear displacements, that is delta 1, delta 2 and delta 3. Then once I evaluate, I will put the values of delta 1, delta 2 and delta 3 in equation number 2, and I can get my final strain energy stored in this particular problem. Is it clear? Hello? Hello? Is it clear? Please respond. Please
Yes, sir.
respond whether it is clear or not.
Clear, sir.
Okay. So let us find out the value of delta 1, delta 2 and delta 3. For that, what I need to do individually for each and every element, let us try to draw the free body diagram. So if I consider the first element, this is my first element. The first element is comprising of node 1 and 2. This is node 1 and this is node 2. At node 1, force acting is F1 along positive x direction. At node 2, force acting is F2 along positive x direction. So this is F1 and this is F2. Similarly, displacement of node 1 is U1 and displacement of node 2 is U2. So this is your U1 and U2. So this is the free body diagram of the first element. Now, if I want to write down the linear displacement for this element, how I can write it down? Assuming that the linear displacement for this element, that is for the first element, is how much? Delta 1. Delta 1, 1 represents linear displacement for the first element. It is how much? If I assume that F2, if I assume that F2 is greater than F1, then definitely the nodal point 1 with respect to nodal point 2 will be in compression. If that is the case, then I can write this deflection delta 1 is how much? It is nothing but this U2 minus U1. Since it is compressing in nature, if I assume F2 greater than F1, so I can write U2 minus U1. Yes or no?
Yes, sir.
Fine. We know, so we know that if you are we know that if say I am having a spring, assume that this is a spring, and on the free end of the spring if you apply a force, then after some time what will happen? The spring will come back to its initial position by the help of a force, and that force is known as restoring force, and that is given by F is equal to minus stiffness of the spring, that is K, into the displacement of the string. In our case, the displacement is delta. So let us let us neglect this minus sign. Then the governing algebraic equation for this entire problem is what? It is nothing but F is equal to K into delta. Yes or no? This is the governing algebraic equation for this particular for this problem. Is it okay?
Yes, sir.
Equation number 3 dash.
Yes, sir.
Okay. So I have written down the governing algebraic equation for this problem. Now if I see the free body diagram of the first element, and if I write the equations of equilibrium for this particular element, what I can write? I can write summation fx equal to 0. That means I can write f1 plus f2 equal to 0. So f1 is equal to how much? F1 is nothing but minus times of f2. So let us try to find out the value of f1. We know that the governing algebraic equation is what? It is f is equal to k into delta. So the nodal force at the first node will be F1 will be equal to, for this particular element, stiffness value is K1 into delta 1. Delta 1 is the linear displacement for element number 1, and it will be how much? Now if I consider, now since I am considering nodal point 1, so let us consider now that f1 is greater than f2, because I am interested in getting the value of the nodal force F1. That means I am interested at only nodal point 1. So in this case, let us assume that F1 is greater than F2. If F1 is greater than F2, definitely nodal point 2 will be in compression and nodal point 1 will be in tension. Then I can write this value of delta as what? I can write it as U1 minus U2. If F2 is greater than F1, then I can write U2 minus U1. And if F1 is greater than F2, then I can write U1 minus U2. So I can write F1 is equal to K1 into delta 1. And this delta 1 is how much? Delta 1, that is linear displacement for element 1 from node 1. That is U1 minus U2, which is equation number 4. Is it okay? Any doubt so far till equation number 4?
No,
No,
sir.
sir.
Okay, so please do not get confused with this delta and this delta. Both are same. Way of writing is different. I have written the linear displacement for element number 1, that is delta 1, by considering that F2 is greater than F1. If I look from node 2, then it will be U2 minus U1. But if you look from node 1, then in that case F1 is greater than F2. If you assume, then I can write it as U1 minus U2. Is the two term clear? Why this is U2 minus U1 and why this is U1 minus U2? Any doubt? Hello.
No, sir.
Okay. Next, then since we have found from equation number 4 gives us what? Gives us the value of F1. From equation number 3, I know that F1 is what? F1 is minus times of F2. So F2 will be minus times of F1. That means minus times of K1 into U1 minus U2. So if I multiply this minus inside, it will be K1 into U2 minus U1. See, when you consider force F2, that means you are looking from node 2. It is K1 into U2 minus U1. And when you consider node 1, that is force F1, when you are looking from node 1, then F1 is greater than F2. It is K1 U1 minus U2. So is this equation number 5 and equation number 4 clear to you?
Yes, sir.
Fine. So F2 is K1 into U2 minus U1. Similarly, for second element as well as for third element, let us find out the displacement delta 2, linear displacement delta 2 for second element, and linear displacement delta 3 for third element. Let us find it out. Similarly, for second element, if I assume that F3 is greater than F2 for the entire element, then I can write delta 2 for the second element is U3 minus U2. Then this point will be in tension and this nodal point will be in compression. Yes or no? Delta 2 2 is equal to U3 minus U2. Any doubt? Hello? Any doubt so far? Okay, since no one is responding, so I will assume that there is no doubt. So then for element number 3, similarly, I can write deflection delta 3 for element number 3 is how much? It is U4 minus U3. If F4 is greater than F3. But if F3 is greater than F4, the equation becomes U3 minus U4. Since if we have assumed that F4 is greater than F3, so equation is delta 3 for third element equal to U4 minus U3. Is the step clear? This one? Hello? Hello?
Yes, sir, clear.
Okay. So we have found out the linear displacement for all the elements. We have found out the linear displacement for all the elements. That means we got the value of this delta 1, delta 2 and delta 3. Delta 1 is for element 1, delta 2 is for element 2, delta 3 is for element 3. So in place of delta 1, what I will write? I will write U2 minus U1 whole square. In place of delta 2, I will write U3 minus U2 whole square, and in place of delta 3, I will write U4 minus U3 whole square. Then the resulting expression of strain energy becomes U equal to half K1 U2 minus U1 whole square plus half K2 U3 minus U2 whole square plus half K3 U4 minus U3 whole square. Equation number 6. Is it okay? Any doubt so far?
No, sir.
Okay. So in order to find out the value of this potential energy pi, we have calculated the value of U. Next, what is left? Next, this one is left. That is total external work done by external force on the system. I have told you, if you remember in some previous classes, that external work done consists of three components. One component is traction component, another component is body force component, and the third component is work done due to point load. So by looking at this diagram, can you tell me that in this problem which component of work done is there by the external force? Whether it is a traction component is given, or body force component is given, or a point load component is given. Which component will I take to find out the value of total work done W? What I will take? Since by looking at this problem, it is very much clear that the external work done by the external force comprises of only point load. You can see only point load is acting at nodal point 1, nodal point 2, nodal point 3 and nodal point 4. So these point force are only responsible for the total work done. And that total work done will be given by what? Will be given by force into displacement. That means it will be minus, this W will be what? W will be minus F1 U1 for first node minus F2 into U2, because force into distance will be work done, F2 into U2 for node 2 minus F3 into U3 for node 3 minus F4 into U4 for node 4. So the final expression becomes pi is equal to, this is equation number 6, that is the value of u minus w. W is what? W is nothing but equation number 7, that is minus f1 u1 minus f2 u2 minus f3 u3 minus f4 u4. Is it okay so far?
Yes, sir.
Okay, so this is equation number 8, which is the modified potential energy or potential of the problem in terms of K, that is stiffness of the spring, U, that is the linear displacement of the spring, and force, that is nodal forces. Fine. Now, so we have found out the value of phi. We need to find out the value of the global stiffness matrix by principle of potential energy approach. We know that in potential energy approach, we need to minimize this potential energy pi. How we can minimize? That also we know. We can only minimize if we partially differentiate equation 8 with respect to, if I differentiate partially equation 8 with respect to displacement ui. What is I? I is the nodal point where the displacement is occurring. But if you remember in Rayleigh rates method, here I have taken del pi by del some constant value equal to 0 in Rayleigh rates method. Fine. But here I am taking del pi by del ui equal to 0. Why? Because if you see this equation number 8 only varies if u vary. If u does not vary, equation number 8 will not vary. That means equation number 8, that is pi, is a function of u. So in order to minimize the total potential energy, what you will do, you have to partially differentiate equation number 8 with respect to ui. I is the number of nodes where the displacement is acting, and then you have to equate it equal to 0. Since we are having total 4 nodes, node 1, node 2, node 3, node 4, so there will be 4 cases. First case is when del pi by del u1 equal to 0. Second case, del pi by del u2 equal to 0. Third case, del pi by del u3 equal to 0. And the fourth case, del pi by del u4 equal to 0. So, 4, that means if you partially differentiate it, you will get 4 different equations in terms of f, k and u. Then from those equations we will write the final assembled stiffness matrix. So far is the process clear? Any doubt so far?
Yes, sir. Clear.
Okay. So let us partially differentiate equation number 8 with respect to u1. So del by del u1 of equation number 8, which is equal to 0. So del by del u1 of half k1. This is a minus b whole square, that is a square plus b square minus 2ab plus partial differentiation of this particular term will be 0. Partial differentiation of this particular term will be 0 because there is no u1 present. Similarly, partial differentiation of this term will be 0. Partial differentiation of this term is 0. This term is also 0. This term is also 0. And partial differentiation of this expression is minus f1 del by del u1 of u1, which is minus f1. So del by del u1 of this quantity minus f1 is equal to 0. Now if I partially differentiate this expression, I can take this half k1 common of the bracket, half k1, then del by del u1 of u2 square plus u1 square minus 2 u1 u2. So u2 square again it will be 0. There will be no partial differentiation. u1 square will be 2 times of u1 minus 2 u2 del by del u1 of u1 is 1. So minus 2 u2. Or I can take 2 common. If you take 2 common, this 2 and this 2 will get cancelled down. Your final expression while substitute for case number 1 becomes f1 is equal to k1 u1 minus u2, equation number 10. And what is this f1? This f1 is nothing but the nodal force acting at nodal point 1. Is it okay? Equation number 10.
Yes, sir.
Similarly, you will get, if you partially differentiate del pi by del u2 and equate it equal to 0, you will get one expression in terms of f2. For del pi by del u3 equal to 0, you will get one expression in terms of f3. And for del pi by del u4 equal to 0, you will get one expression for f4. So for case 2, that is del pi by del u2 equal to 0, what we will do? Del by del u2 of this is pi, okay. So del by del u2 of, in bracket, partial differentiation is possible for this term. So half k1 a minus b whole square, that is a square plus b square minus 2ab plus del by del u2 of, yes, we also have to do the partial differentiation of this term because in this term u2 is present. So plus del by del u2 of half k2 comes out of the bracket. Then a minus b whole square is what? That is a square, that is u3 square plus u2 square minus 2 u2 u3. Fine. Partial differentiation of this term is 0 because we are interested in only displacement u2. Similarly, partial differentiation of this is 0, this is 0, and this is 0. Ultimately, del by del u2 of minus f2 u2 becomes minus f2. So the final expression becomes k1 u2 minus u1 plus k2 u2 minus u3 equal to f2. That is equation number 11. Is it okay?
Yes, sir.
Okay. Other people, please respond whether it is clear or not. Other people, please respond whether it is clear or not.
Yes, sir, clear.
Okay, fine. Next is, so for the third element, del pi by del u3 equal to 0. For the third node, del pi by del u3 equal to 0. That is del by del u3 of pi. This is pi del by del u3 of pi. That means partial differentiation of this term is 0. There is no u3. Partial differentiation of this term is possible, but before that I have to expand it. That is del by del u3 of half k2 into u3 a minus b whole square, that is u3 square plus u2 square minus 2 u2 u3 plus partial differentiation of this term is also possible. U3 is present. So del by del U3 of half K3 U4 minus U3 whole square, that is U4 square plus U3 square minus 2 U4 U3 minus this term will not come into account, this term is also not will not come into account, and this term will also not come into account, because in all these terms u3 are not present. So ultimately the partial differentiation of del by del u3 of minus f3 u3 is how much? It is minus f3, which is equal to 0. So once I partially differentiate this expression, so I will get what? I will get the value of force F3, that is K2 U3 minus U2 plus K3 U3 minus U4 equal to F3. That is equation number 12. Is it clear? Is it clear, equation number 12?
Yes, sir.
Okay. Other people please respond whether equation number 12 is clear or not. Other people please respond whether equation number 3 is clear or not.
Yes, sir. Clear.
Okay. Next is for the fourth node. For the fourth node, partially I will differentiate the potential with respect to the fourth displacement, that is del by pi by del u4 equal to 0. That is del by del u4 of pi. This is pi. Already we have calculated. So in this expression, partial differentiation of this term is not possible. U4 is not present. Partial expression of this term is also not possible. For this term, partial expression is possible. That is, for that, what I have to do? I need to open this bracket. How I will open? That is del by del u4 of half k3 a minus b whole square, that is u4 square plus u3 square minus 2 u4 u3 minus partial differentiation of this term is not possible, this term not possible, this term is also not possible. Ultimately minus del by del u4 of f4 u4, that is minus f4 equal to 0. So if you partially differentiate it, you will get the expression of f4, and that expression of f4 comes out to be k3 in bracket u4 minus u3, which is equation number 13. Is it clear? Any doubt?
Clear, sir.
Yes.
Fine. Next, what I need to do, since I have to frame a matrix, so first what I will do, I will rearrange these equations. Which equations I will rearrange? I will rearrange equation number 10. That means I will just open the bracket. It will f1 will become k1 u1 minus k1 u2. That means we will separate the terms. With u1 we will separate the terms, u2 we will separate the terms, u3 individually we will separate, and u4 individually we will separate. Similarly, for equation number 11, we can rearrange and write like this. F2 is equal to K1 U2 minus K1 U1 plus K2 U2 minus K2 U3. Now take common. So after taking common, equation number 11 becomes this expression, that is F2 is equal to minus K1 U1 plus K1 plus K2 into U2 minus K2 U3. Similarly, equation number 12. Again, F3 is equal to K2U3 minus K2U2 plus K3U3 minus K3U4. Take the common value, common term of U. So if you take common, this is the expression F3 is equal to minus K2U2 plus K2 plus K3U3 minus K3U4. Similarly, for the fourth expression, this is my fourth expression. So F4 will be equal to K3U4 minus K3U3. That is minus K3U3 plus K3U4. That is equation 14, 15, 16, 17. Is the thing clear to you? Equation number 14, 15, 16 and 17?
Yes, sir.
Fine. Okay. Now if you see this expression, which expression? 14, 15, 16, 17. This is nothing but it will this is it is looking like a governing algebraic equation of the form f is equal to k into delta. This is f, this is nothing but f is equal to k. K is present in each and every expression into delta. This is the final governing differential equation. I know. Fine. Sorry, final governing algebraic equation. So in matrix form, I can write matrix F is equal to matrix K into matrix delta. Now, what is this K? K matrix is known as global stiffness matrix or final assembled stiffness matrix, which I need to find out. What is delta? Delta is linear displacement vector. It is linear displacement matrix vector. And what is F? F is linear nodal force vector. Linear nodal force vector. Fine. So in matrix form, how I can write? See, if you see in the entire problem, total 4 nodes are there. Total 4 nodes are there. You keep in mind that whenever we use this matrix method to solve the problem, the final stiffness matrix, normally the final stiffness matrix, the size of the matrix will be equal to the number of node present in the given problem. Here total 4 nodes are present, so the size of the final stiffness matrix will be 4 by 4 matrix. It is a 4 cross 4 matrix. So let us write down one. Let us encircle these values: 1 2 3 4, 1 2 3 4. What is these 1 2 3 4? This 1 2 3 4 represent the nodal points. This 1 2 3 4 represent this 1 2 3 4 and this 1 2 3 4. It represents the nodal points present in the problem. Then definitely this first row will be the equation of the first nodal point. The second row will be the equation of the second nodal point. Third row will be the equation of the third nodal point. And fourth row will be the equation of the fourth nodal point. Yes or no?
Yes, sir.
Fine.
Yes,
So
sir.
now leave this matrix. I don't know where it has come. I will tell you. This matrix we have made and this 1, 2, 3, 4 we have written into. There are total 4 displacements. 4 nodes are present. 4 displacements are there. So that is U1. At first node, displacement is U1. At second node, displacement is U2. At third node, displacement is U3. At fourth node, displacement is U4. Check from the problem. First node displacement U1, second node displacement U2, third node displacement U3, fourth node displacement U4. So I have written in, it is a column matrix. It is a column matrix because this is first node, the second row is second node, third row is third node, fourth row is fourth node. Equal to, again it will be a column matrix force vector. That means first row represents the nodal force acting at the first nodal point, which is F1. Second row represents the force acting at the second nodal point, which is F2. Likewise, F3 and F4. F3 is for third nodal point given in the problem. F4 is the force acting at the fourth nodal point given in the problem. See, for first nodal point F1, second nodal point F2, third nodal point F3, fourth nodal point F4. Is it okay? Is this matrix clear? This column matrix U1, U2, U3, U4 and this matrix F1, F2, F3, F4. I haven't talked so far. I haven't talked about this particular matrix. This U1, U2, U3, U4 and F1, F2, F3, F4. Is it clear to you? And this outline 1, 2, 3, 4, 1, 2, 3, 4. Is it clear so far?
हाँ जी सर. Yeah.
Yes, sir, clear.
Okay.
Yes.
Now in B, now this matrix, I know that this is which matrix? This is K matrix, which is the assembled stiffness, or the other name is global stiffness matrix. Other name is global stiffness matrix. That means this matrix is for the entire problem. Into this is what? This is displacement vector matrix, and this is what? This is force vector matrix. How I will get this expression? See, I will get it from equation 14, 15, 16, 17. In coefficient of u1 is what? K1. So write down K1. Coefficient of u2, because this first row represents what? First row represents equation of f1. So f1 is equal to k1 u1 minus k1 u2. So this is k1 because this is nodal, this because this is my wait, let me write. This is u1, this is u2, u3, u4. Similarly, this is u1, u2, like this. If I write, it won't, there will not be any mistake. Fine. So I can write k1 minus k1. There is no u3, neither there is u4. So it will be 0, 0. K1 minus k1, 0, 0. Is the first row clear? Is the first row clear? Hello? Hello? Is the
Yes, sir. Clear.
first okay. Similarly, second row represents the equation of force F2. We have F2, that is minus K1 U1 plus K1 plus K2 U2 minus K2 U3. Coefficient of U1 is minus K1, so it will be minus K1 minus K1. Then K1 plus K2 in place of U2. So K1 plus K2 minus K2 minus K2 0, because there is no U4. So this is the second row. Minus K1, K1 plus K2 minus K2 0. Is it clear? Is the second row clear? Hello? Hello? Is the second row clear? Oh, since no one is responding, so I will assume
Yes, sir.
that it is
Clear.
clear. Okay. Similarly, for third row is nothing but the equation of F3. F3 we have equation number 16 minus K2 U2 plus K2 plus K3 U3 minus K3 U4. That means there is no U1 present, neither the coefficient of U1 is present. So this is 0. Then this is U2, so it will be minus K2. For U3, this will be K2 plus K3. And for U4, this will be minus K3. Minus K3. Similarly, the fourth row represents the equation of F4. F4 is how much? Minus K3 U3 plus K3 U4. So there is no U1, no U2 present. So the coefficients will be 0. See, 0, 0. Coefficient of U3 is minus K3, minus K3. Coefficient of U4 is K3, K3. So this matrix is the resulting assembled stiffness matrix. K1 minus K1 0 0 minus K1 K1 plus K2 minus K2 0 0 minus K2 K2 plus K3 minus K3 0 0 minus K3 K3. Now if you multiply, if you do the matrix multiplication, that means matrix multiplication is how? That means first row into this column. You will get the equation F1. Cross verify it. See, K1 into U1 minus K1 into U2, 0 into U3 is 0, 0 into U4 is 0, equal to F1. So K1 U1 minus K1 U2 equal to F1. See, K1 U1 minus K1 U2 equal to F1. That means you have written it correctly. Check the second equation, whether that equation F2 is coming or not. That means matrix multiplication will be second row into this column. That means minus K1 U1. See, minus K1 U1. Then plus K1 plus K2 into U2. K1 plus K2 into U2 minus K2 into U3 minus K2 into U3 plus 0 into U4. So there is no present, it is not present, which is equal to F2, which is equal to F2. So by this you can cross verify it whether the stiffness matrix which you have generated it is correct or not. So, and this is the final expression which I need to find out for this problem. That is the final assembled stiffness matrix. This is the procedure by which, means by the help of potential energy approach, how to find out the value of assembled stiffness matrix for a particular problem. This is the general approach. I hope it is clear to all of you. Okay? Any doubt? Any doubt so far? Any doubt so far? Hello.
No, sir, no.
Oh
Okay.
no.
So with this, I am ending today's class. Again, we will meet tomorrow for FEM class. We will meet tomorrow at 3 p.m. 3:10 to 4 p.m. Today, within 5 minutes. Again, we will join with the gate class. Whosoever is interested, you can join in that gate class. Fine. So if you have not given your attendance, you can give your attendance and leave the meeting. Thank you.